are now ready to learn one of the major fundamental laws of this course, kind of alongside conservation of energy and Newton's laws. This one is conservation of linear momentum. So this would be what would happen with a system of particles. So if we have an isolated system, so by isolated, we mean that there are no significant external forces, and really we mean external impulses. So external forces acting for significant time. So before we go on, then we're basically going to say momentum's conserved. But before we go on to that, let's take a second and think about this. If we talk about it being isolated, what's going to happen is we're actually going to be able to ignore friction, even between two things sliding along a surface and colliding. Well, friction isn't really a negligible external force, but if it acts for a short time, if the collision is a very short time, then the amount of the change in momentum, the amount of impulse that friction, plays is very small. So we can ignore a lot of these external real life things if we look at a very small time scale. So if we have an isolated system, then what we mean by conservation of momentum is similar to conservation of energy, is that the total momentum of all objects in the system is a constant. So this comes directly from the idea that we ended the previous module with, which is that when two things collide, they experience the same impulse. So the individual change in momentum of both is the same. And if you just rearrange that a little bit, you basically get this statement for conservation of momentum, which is that the sum of all initial linear momentums is equal to the sum of all final linear momentums. So that P final minus P initial of one object is equal to P final minus P initial of the other. But this time what we're doing is rearranging it and reframing it as a conservation law so that all of our initial momentums of all the objects that might be coming in and interacting is the same as all the final momentums added together. So that doesn't mean that in a collision, if something comes in, collides, and this other thing moves, this object's momentum isn't the same before and after. And the second object's momentum isn't the same before and after. What is the same is the total momentum of the system. So a couple important notes about this. This is the total momentum of the system. Another one is that this is back to components. So this involves vector components. Because we can isolate our x components and our y components. So we can write this as the sum of all our initial momentums in x is equal to the sum of all our final momentums in x. And we'd have a similar equation for y. And in a later video, we'll see an example of how to apply that. And then the third thing, and this one is very important, this goes to the idea of it being an isolated system. This conservation law, when we apply it over a very short time scale. It's not like energy. Energy where we're like, oh, something's on a hill, and then it goes over a friction patch, it goes through a loop-de-loop, and then it hits a spring. It's like, who knows how much time took between the two. It could be a very long time, or energy is just somewhere in the universe and we have to go find it. Conservation momentum, because conservation of momentum, sorry, I had a phone call. Conservation of momentum, because it's over this short isolated time scale, then we can only really use it in our problem solving immediately before and immediately after collision. So this is going to here say that it applies over a short time scale to get that impulse from external impulses small. So what that means is that it's an immediately before and after some sort of event of interaction between these. Immediately before and after, what we'll see will be like a collision, two things colliding, or an explosion, like a firework exploding. Collision or an explosion, and we'll apply it again right before and right after. Okay, let me know if you have any questions.